In the earlier lecture on AC circuits, we have analyzed the series and parallel combinations of LR circuits fed by AC sources. Today we are going to take up the corresponding study for CR circuits. As for example, we consider the series CR circuit in which a capacitor of capacitance C and any resistor of resistance R are connected in series, and the combination is fed by an AC voltage source. So to analyze it through EMF equation, we write EMF equation, that is, we apply Kirchhoff's voltage law. And we know that this is R times I, and this is Q by C. To bring our current I, we differentiate it, so this is D. This is the EMF equation. The particular integral, this complementary function is some constant A T by tau, where tau is equal to CR, the time constant. And the PI is, for PI we write the trial solution as I is equal to I0 e to the power j omega t, because the characteristic oscillations or characteristics dynamics of the circuit in absence of the source dies down exponentially, and the circuit ultimately oscillates in tune of the applied voltage. So we assume this is to be the solution where I0 may be complex and has to be found out. So the first equation is j omega V0 plus V0 by C whole thing multiplied by j omega t, and on the right side j omega V0 e to the power j omega t. If we divide both the sides by this part, j omega times this, we get this is, I have written, this is I0, this is I0, so we get I0 taken common, so we divide it, this part goes, and j omega, this is R plus 1 upon j omega C is equal to V0, or V0 is equal to V0 is equal to ZI0, where we define Z, the impedance for CR circuit, as R plus J omega C. Sorry, this J is in the denominator, so the sign will be minus. This is the impedance of CR circuit. The complex impedance, which we can write as mod z times e to the power minus j phi, where z is defined as r square plus 1 upon omega square c square square root, and tan of phi is equal to 1 upon omega c by r is equal to 1 upon omega cr. Now if we write current, expression for currents, and current becomes I0 is equal to V0 by Z. So this is V0 by mod Z times e to the power minus j phi. So this is equal to V0 mod Z e to the power plus j phi. So this is the peak expression in terms of peak voltage, peak current, and the instantaneous current is given by so we see that the current leads over the applied voltage by a phase angle phi, which is governed by this. We can also write this equation in terms of Xc. One defines Xc, the reactance of the capacitor, is thus. So this can also be written in terms of Xc. Simply this is R square plus Xc square. Now the phase angle, phase phi, is at omega is equal to 0, it is infinite, so phi is pi by 2. And as omega becomes very large, this part becomes 0, so phi is 0. So the variation of phi is from pi by 2, this is omega. This is the variation of phi. And if we want to find out the reason physically, which will be very much clear from the Phasor diagram that I am going to discuss right now. This is the series circuit. So if this is be the this is the current at a particular instant, this is the current phasor, and this is the corresponding VR phasor. VC lags behind the current, so this is the VC phasor. This is R times I, and its magnitude is XC times I. So this is the applied voltage V phasor, and this is the I phasor. This angle is phi. So the current in shear circuit leads over the applied voltage by a phase angle phi. Now you see that this magnitude is R times I, and this magnitude is where I am neglecting the negative sign because I have already drawn it in this direction. So this is as omega is 0, this part omega tends to 0, this part is very high, so this part is very high, and the current, the phasor angle is pi. The phase angle is pi because this vector then becomes almost parallel to this, and this is the angle phi. And when omega is very high, this becomes very small, and this resultant becomes almost co-parallel to this. So which explains the variation of phi with frequency. Now we come to the current gains. Current gains. So we have solved the problem in two ways. One is by using the EMF equation, and another one is the Phasor diagram method. The current gains are GVR of omega, this is as usual VR by V phasor, its magnitude, so this is Ri and this is Zi. So this is R upon modulus of Z, and for this we write modulus of Z is R square plus 1 upon omega square C square under root by R. If we multiply all through by omega C, we get it as omega CR by 1 plus omega CR whole square under root. We see that as omega is 0, this is 0, and as omega tends to infinity, this tends to 1. And the voltage gain across the capacitor is proceeding similarly, we find that this is so if you see the variation of this two, we write a gain curve, voltage gain. This is frequency axis, this is the voltage gain, this is the one line. At omega is equal to 0, this is 0, and at omega tends to very high value, we can neglect 1 in presence of the high quantity and this becomes 1. So this is GVR. At omega is equal to 0, this is 1 and this goes to, this is GVC. So it's clear that if we measure the voltage across capacitor, it behaves as a low pass filter, and if we measure the voltage across resistor, it acts as a high pass filter. This is the cutoff frequency, omega C, and at omega C we see that since denominator are the same, omega C CR is equal to 1 or omega C is equal to 1 by tau, the time constant. This theory has been implemented in one of the experiments of CU electricity magnetism course. This filtering action has to be studied, and one has to identify the cutoff frequency, and from that we can calculate time constant. Somebody suggests that to find out the maximum value of GVC and go to 1 by root 2 time of its value, and such a question has also been set in Calcutta University examination in the previous years, in yesteryears, but it is not a right way of identifying the cutoff frequency, because to know the maximum of this, one must go to the zero frequency limit, which is not practicable. So what is the right way is to draw both the gain curves on the same paper with the same scaling, and from the intersection point of the two gain curves one can get the omega C in a right way. And Another thing is that although a capacitor, ideal capacitor is assumed to be one which has no resistance, but in practice the real capacitor is a combination of the as a combination of a pure capacitor of capacitance C together with a small series resistance RC. So a real capacitor and the combination can be assumed to be act as a real capacitor. Earlier we have studied that in a capacitor there is no energy loss over a cycle. So in 2 quarters capacitor receives energy from the source, and in other 2 quarters it rejects energy or returns the energy to the source. But when we have a real capacitor, there is a lossy element, resistance is there, and energy is dissipated across this resistance. So it will found that if this is be the current phasor, and the instead of the capacitive voltage, instead of being at 90 degree apart from it, it deviates from 90 degree by a small amount, and this is known as the loss angle for the capacitor. The loss angle is a measure of the resistance RC, and it also is a measure of the amount of energy that is being dissipated in capacitor due to its imperfection. In a shear circuit, we can estimate the resistance like this. For a pure circuit, pure C, the circuit diagram is the phasor diagram is this. This is VR, this is VC, and this is V, applied voltage V. This is the phasor diagram in the case of a pure capacitor. For real C, the graph becomes like this. We take a particular frequency and measure the VR, VC and VB. To measure VR, we connect the RMS meter over this. To measure VC, we measure this RMS meter across the capacitor, and this gives you the V. We first make a appropriate scaling, and this represents the VR. Then from this we take the arc proportional to the magnitude of VC, said, and from here we take a arc proportional to V. This is V. This is the effective VC, and if we draw a perpendicular line, then this is a measure of the loss angle across capacitor. There are 2 other important applications of this circuit, that is the integrator and the differentiator. Let me come to the current expression. The current expression is the I is equal to V upon R minus J omega C. This is the current expression for current in a series CR circuit. For low frequency, or first consider high frequency. High frequency, this part is negligible, so I at high frequency is approximately equal to V by R. Here V is the applied voltage. If we now consider the voltage across the capacitor, the voltage across the capacitor is Vc, Q by C, or if we write it in terms in a slightly different way, we get the voltage across this, which can be written is this, which can be written in a slightly different way, is IC dt. For I, since it is a series circuit, same current flows through it, and for I we write this approximate value, so we get 1 by CR V dt. This is the applied voltage, and this is the output voltage across the capacitor C. This is the applied voltage or input voltage. So this circuit shows that the output voltage is an integration over the input voltage. So this circuit in the high frequency range behaves as voltage integrator. An integrator is a circuit which delivers the output as the time integration over the input. Here the input voltage is the applied voltage, whose time integral is the output voltage across the capacitor. So this circuit, if we measure the voltage across the capacitor, it behaves as a voltage integrator. On the other hand, for low frequencies, we can neglect this term, and this J will be on the for low frequency. This part is very high, so we neglect R, and this is the result. And if we measure the voltage across the resistor, the voltage across the resistor is Ri, and for I we use this expression J omega CV. Since this is a sinusoidal voltage, we know that this is, I have missed R. Since we know that is a sinusoidal voltage, we can write it as dV dt. So here it is again the applied or input voltage, and this is the output voltage. And if we measure the voltage across resistor, it behaves as voltage differentiator. There are the three, so the series circuit can have filtering action. Apart from this, they can be used as voltage integrator and voltage differentiator. Now we come to the parallel shear circuits. I am not going to detailed calculation of this. I will just outline the main steps, and the detailed calculation are available in the notes specified to you, or notes supplied to you. Sorry, notes supplied to you. parallel CR circuit. The circuit is fed by an AC source. So current I, and this current breaks is split into two parts as per Kirchhoff's current law. This is IC, this is IR. If we write the current equation or differential equation, if we go to the differential equation formalism, this is IR plus IC is equal to I is equal to I0 e to the power j omega t. I is equal to V by R, and IC, we know that in a capacitor Q is equal to CV, so I is equal to so this part is C dV dt omega t. If we want to solve the CF for this particular complementary function, this is V by R plus C dV dt is equal to 0, which gives you dV by V is equal to minus minus 1 upon CR dt. This is minus dt by tau. So V as a function of t is some constant e to the power minus t by tau. So again, for parallel combination 2, the complementary function dies exponentially with the time constant, can have the same time constant. This is very important. And for PI particular integral, we see that the voltage ultimately oscillates in tune of this. So we write V as a function of t is equal to V0 e to the power j omega t, where V0 is a complex quantity which requires to be obtained. Here you get 1 by R plus j omega c V0 is equal to I0. Or we write j omega c. Where Y is the admittance, which we have also introduced in the case of LR circuit. Tan of theta is equal to omega CR. We will compare this with the result obtained in the case of series circuit. This is the series circuit. The phase is pi, and here we have used the phase as theta. So the phase relation is also reciprocal to each other. From here we get that V0 is equal to I0 mod y e to the power minus j theta. So in terms of instantaneous values, we write V at time t is equal to I0 mod y that is V lags behind current. Let me verify this from the Phasor diagram. This, let at a particular instant, this is the voltage, so this is also the current phasor across this, across the resistance. And it is the current phasor across inductance. And if we complete the parallelogram, here it is rectangle, I get it is the I, the current, which is Y times V phasor that I have introduced here. I is equal to YV. So this angle is theta. You see that current is ahead of voltage in phase, which is just this relation. The voltage lags behind the current, and here also we can define the current gains. The current gains if we measure the current across C and R by 2 RMS meter, we define this is I for current and R is the cross race. So this is IR by I phasor this expression V cancels out. We know the expression of Y. You recall that magnitude of Y is 1 by R square plus omega square C square under root, and this if we multiply by this, it becomes 1 by and similarly we can define the current gain across the capacitor. And on simplification, this this is the expression, and we see that at omega is equal to 0 this is 1, and as omega goes to infinity this goes to 0. At omega is equal to 0 it is 0, and as omega tends to infinity this tends to 1. So here also we can find the filtering action. Current again, this is one line. This is for GIR. This is GIC. Here from we can also define omega c, which is again equal to the time reciprocal of the time constant. So by this we end our discussion on series and parallel CR circuits. In the next class we shall consider LC circuits, which is not very conventional, but still we shall, to complete the cycle of discussion, in the next class we shall consider the series and parallel combination of LC circuits fed by AC sources.